This assessment asks us to predict the mechanism for the Robinson annulation reaction. This mechanism will start with sodium hydroxide acting as a base to form an enolate, so it'll attack this hydrogen. That'll break the carbon-hydrogen bond and form the carbon-carbon pi bond of the enolate, break the carbon-oxygen pi bond, pushing electrons onto oxygen. That will form our enolate intermediate. The enolate can react as a nucleophile and will react with our alpha-beta unsaturated carbonyl as an electrophile. The electrons from oxygen will kick down to form the carbonyl. That will allow the enolate carbon to act as a nucleophile, react with the beta carbon of the alpha-beta unsaturated carbonyl, and push the electrons up into oxygen of the electrophile. That will form one of our key carbon-carbon bonds in this process. It will also form an enolate intermediate. Now, eventually, we need this enolate to swing back around and attack the original carbonyl, but we need the enolate to be on the other side of the oxygen. So we need to do a little bit of proton shuffling to get the enolate on the other side. So we'll take this enolate and we will protonate it with water to form a carbon-hydrogen bond and reform sodium hydroxide. This sodium hydroxide can then deprotonate the alpha proton on the opposite side to form an enolate on the other side of the carbonyl. This enolate can now attack our original carbonyl to form our second key carbon-carbon bond. This alkoxide can be deprotonated and then eliminated. So we'll use water to protonate this intermediate. And then we'll do our beta elimination. So we will reform an enolate with more hydroxide. And then we can use this enolate to eliminate the OH group and form our final product. These electrons will drop down to form the carbonyl. This double bond will swing over to form the unsaturation, kicking out OH minus as a leaving group, and that gets us to our final product. This is the mechanism for the Robinson annulation reaction.